Hello. Let's start. So you must have received your marks for assignment, the programming assignment. I don't remember the number. Number 3. Right? So you must have received it. We are grading your non-programming assignment, and you will, by end of this week or early next week, you will receive marks for that as well. Today, after the class, some of the TAs have allocated a scheduled time to meet you about your questions, and so that you can meet them after the class. So today, it's not about the midsem. We will start with the new topics from now. Okay. Your project proposals also, we have received your project proposals. We will also grade it very soon and give you back your comments. So today onwards, so next half of this semester, we will focus on wireless networks. Right. I have borrowed some of the slides from IIT Bombay, and these are the ones. So we will use these slides. I will post either link to the slides on the backpack so you can download these slides. So anybody remembers why we are learning wireless networks in this course? We discussed a reason, a very good reason why we need to learn networks. By definition, mobility, you get mobility only when you are wireless, right? With wired, there is no mobility. So to write better programs, to understand what your programs can do, it's good to have, I'm not saying you should be an expert in wireless network, but you should know what wireless networks are. Because as years will pass by, most of you will only use wireless. We already have lots of laptops these days, which only pretty much work on wireless, right? Otherwise, there's no other thing. Right? Very soon, the broadband will also be on wireless. We already have live TV on phones now, right? So very soon, your TV, you will not get a digital connection. It will be wireless from the day one. So some of you have taken networks course with me. The approach in the networks course was we started with application layer, and then we went one layer at a time below, and we stopped at the MAC layer. In this course, we will reverse the flow. We will reverse the direction. We start with the bottommost layer, which is the physical layer, and we will start going up, and we will stop at the MAC layer. And then I will introduce something about the IP layer. It will not go all the way to the transport layer, and because transport layer is the same. It's pretty much the same. TCP and UDP, wired or wireless, is the same. Application layer to some extent is also the same. What changes drastically is the physical layer and the MAC layer. Right? So we'll focus on that, and then we'll focus a little bit on the IP layer, the network. So to get quickly started, we are going to use electromagnetic waves. Whenever we say wireless communication, these are the electromagnetic radiations or waves that we transmit. Right? In optical communication, you send the light. Right? In any of the metallic communication, the copper, coaxial cables, and so on, or wired Ethernet, you actually send the voltage across. And you have a cable, a metallic cable, and you put some voltage on this end, and you will, if the conductivity is good, you get that voltage on the other side, and you communicate through that. This medium uses electromagnetic waves. It's not light, and it's not also voltage. So if we look at all the different bands that are available, and we see the frequencies, we start with low frequencies like 30 Hertz. We call them LS, MS, and HF. If you see the old analog TV, right, you see VHF and so VHF, UHF, right? You see and configure the old analog TV. So in this frequency band, what we say the low frequency, medium frequency, and high frequency, you get 30 Hz to 30 megahertz of frequency. You already know from the physics how to get the wavelength, right? So the reason we are interested in wavelength is because the antenna that you would use to receive this signal or transmit this signal is a function of the wavelength. As your frequency increases, what happens to the wavelength? It increases or decreases? How many says, right? I'm not hearing one word. How many say increases frequency? Frequency with low frequency as compared to the high frequency, right? The wavelength is more or less. More? How many say more? How many say less? I should have inversed. Alright, so as you see, the wavelength is few kilometers, meters, right? And then your antenna depends on that. So you see, it is mostly used by military or submarines when they want to do underwater communication, right? You see, these are the devices which can afford to have that big of an antenna, right? Typically, that's why this is used here. What is the advantage of this low frequency band? It goes to a very long distance. That's a single most advantage of using this frequency. In fact, right, if you're sitting on one point on the earth, right, you can actually transmit it and the signal can go around the earth and come back to you. It has that much of communication range. You can actually get it, your own signal, but it has traversed the entire earth. And because we have the atmosphere, the signal bounces, 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 and comes back. So that is this frequency. So the advantage is the distance you can cover is large, but the disadvantage, one of the disadvantages is you need a long antenna. Then we have this frequency range, which starts from 30 megahertz to 300 megahertz, and this is few meters. And then you have ultra high frequency, which is 300 to 2 gigahertz. Right? So this was used by analog TV. And now we are actually getting rid of this. So why is government getting rid of analog TV? Can you guess from this table, what do you think? What is the reason? Is it because analog quality is bad and government wants you to watch very high quality videos? Is that the reason or something else? Right, they want to free up this whole band, right? And they can auction this band for other people for commercial use, right? And they can get money out of that, right? So that's why they want to get rid of this, and slowly they are doing it. Then you have this one, ultra high frequency, which is 300 megahertz to 3 gigahertz, right? So this is typically used by digital TV, Wi-Fi, and cellular networks, right? So this is where mostly we will look at this band. And then you have super high frequency, which is 3 to 30 gigahertz. Right? It's few centimeters. So, right, the advantage of this is you can get away with a very fine small antenna. Right? So, the device size can get smaller and smaller. As you go to this frequency, the device can become smaller and smaller and smaller. Right? And this is now being tried out for Wi-Fi and satellite using. So this is how you see the whole spectrum, all the way from 30 Hz to 30 gigahertz. And typically we will operate from this source in different communication protocols with cellular and Wi-Fi, which is about 3 gigahertz. Questions on this? Okay, so as I said, when you want to choose a spectrum, what you look at first thing is how much antenna size you can have. Right? You can afford, and of course you can mount it on your device. Right? So the lower frequency need longer because it has longer wavelength, and because of that it has longer antennas, and then the cost will increase accordingly. Another thing is multiplexing of users. So 2 users using the same frequency bands would interfere and they talk at the same time. So you would need some regulations. So if you today want to use that band where digital TV is being used, you cannot use it because you will interfere with the TV communication. Or right, if you want to use the band which is used by analog TV, and in some part of India we're still using the analog TV, right, you will interfere with that. So you cannot freely, even if you own your device and you own the antenna and everything is your own, right, but you cannot freely start transmitting at any frequency. At some bands you will interfere with the military. Right? So you have to think about how many users are already there and how you would interfere with them. And propagation characteristics. As I said, lower frequencies propagate better. Lower the frequency, your communication is long distance because the propagation is better. As you start increasing the frequency, right, it gets smaller. So, for example, this band propagates long distance around the Earth, right, and that's why it is favored by military and those kind of entities. This is VHF is reflected by the ionosphere, and higher frequencies typically need even the line of sight. As the frequency increases, so if I am in a very high frequency band, my transmitter and receiver should be pointing to each other in a line of sight, exactly like this. Even if there is some separation in any of the XYZ plane, I will not be able to communicate, right? So these three things will finalize. If you want to design your own network, right, you have to think in terms of these three properties, and then you decide what you want and what you don't want, and then accordingly choose something. Cellular communication, 800, 900, that band, 1800, 1900. So actually, the 1200, where I'm missing, this slide is missing 1200. But in the world, there are 4 bands that are being used. One is 800, I would say some plus something, then 1200, then 1800, and then 2000. If you have a quad band phone, that means that your phone can understand all these 4 bands of frequencies. You can use your phone in any part of the world, because every country would use some other frequency. This is the standard one. The Wi-Fi, so what I've written is UGN, and now we have AC also. It all uses 2.4 and 5 gigahertz. This is mentioning only 2.4. So what was the challenge in getting this band? What do you think would be a challenge? When the industry people decided we will use this band, what was the reasons? Why? When they first came up with Wi-Fi, why did they choose 2.4? What do you think went through their mind and decision to use 2.4 gigahertz? Smaller antenna size, right? What is the other one? You don't want your laptops and the antenna sticking out, which is pretty long, right? Like the old radios, you just pull it up, right, and stretch it. You don't want that, right? So antenna size is one. What is the other factor? So I have given you all the reasons here. So you think about the reasons, and you already also know that it is being 2.4 gigahertz. And if you want, I can go back one slide and show you the properties of 2.4 gigahertz. So antenna is already we talked about, right? So what is the other reasons for 2.4 gigahertz? Anything about multiplexing? Anything about propagation? I know you're back from a big long vacation, right? So you might need some time. What about, let's see this one, propagation characteristics. What is nice about 2.4 gigahertz? Yes? Yes, very good, right? You don't want to transmit at some frequency here and some other corner of the Delhi, right? Somebody in Dwarka receiving this signal, right? You don't want this way of communication. If you use a very low frequency, right, your signal will just, once it is out, it is out. You cannot control the signal. right? Once it leaves your antenna, then it's very costly to right, make this or contain this signal within some meter, right? You just propagate, right? So that is the reason. Typically, we want Wi-Fi inside your house or inside this room or inside in an auditorium, right? You don't want signal to just float around and go across the city. Right? That's the other reason. What is the other reason? What is this reason? Can you think of a reason as multiplexing of users? What is special about 2.4 gigahertz where you can do multiplexing? You want multiple people to use your band. You don't want one person using Wi-Fi and then you give the Wi-Fi to another person. You want hundreds of people to simultaneously use this. So how would you use this? That's right. A lot of people, and within even you start allocating. Before allocation, you don't want anybody already using this band. And you don't want TV, cellular communication, military communication, or radio communication already using. So 2.4 gigahertz is a band which is empty globally. No matter in which part of the world you are, which country, wherever you are, no government uses 2.4 gigahertz for anything. Right? They have made sure, or they have ensured nobody is using this band, so that you can carry this laptop to any country and you use the same band. You don't need another antenna in your laptop for another, right? As you see in the cellular, right? If your phone only supports this and you go to a country that supports this, your phone is useless. And no matter how much money you have, your phone becomes useless. Here, right, you don't want this thing to happen. So that's why it's globally ensure that no government is going to use this time, right? So that means you will not interfere with each other, and we will see how you can have multiple users using the same line. Do you know anything other than Wi-Fi that uses 2.4 gigahertz? Microwave interfere in that range, and microwave don't want to use 2.4 gigahertz. They don't communicate. Bluetooth, yes, Bluetooth uses 2.4. Reason is the same as for Wi-Fi. What is the other one? Zigbee. Your cordless phone, right? Old days at least, your cordless phone would also use 2.4 gigahertz. Right? So these are the modes of communications, right? And all of them use 2.4 gigahertz for the same, all these three same reasons. Right? So this gives you good balance between antenna size, propagation, and multiplexing of users and so on, right? So that's why it becomes ideal, right? They are not used 2.4 gigahertz for the sake of it. And there were good reasons, and these are the ones. So what does an antenna do? Antenna, the job of the antenna is to send out signal outside and receive the signal, right? Transmission and reception. Right? So different types of antennas, we will not go into details of this. Your EC colleagues, your batchmates will go inside and very much in detail about what this different antenna are. And so isotropic antenna is something which radiates equally in all directions. Right? So that means it's circular, it's sphere, not even circular, it's spherical. Right? So it goes into all the directions. This is the ideal thing that we want, but we don't have an antenna that can achieve this. Right? So what do we have? We have simple dipole antennas, which is omnidirectional in one plane. So in this plane, it propagates everywhere, right? And in the other two planes, right, it has 8-like characteristics, right? So this is one plane, this is another plane, and then the other plane. So X, Y, Z. So in one direction, it will go everywhere equally, and other two planes, it will have 8-like characteristics, right? So it has circular one, right? So other than that, this is dipole antenna. Then you have a directional antenna. It is focused only in one direction. Anybody knows an example of directional antenna? You see a directional antenna? This is the antenna, right? They actually, because of that structure, convex structure, right? They focus and zoom in signal, and you send it. And another point, you have to align these 2 points so that they can, like, if you mount an antenna on top, rooftop, right? You have to mount it such that you get the maximum line of sight. So that's the directional antenna. Then you have antennas, which is the combination of multiple directional antennas, right? And these days you have smart antennas, because you have everything: smartphone, smart refrigerator, smart TV. So antenna also decided to become smart, right? So you have smart antennas, which can actually steer, depending upon where you are getting the signal. The antennas move, right, and gives you maximum coverage. So you don't have to tune these things. As I said, more of these things in maybe Shobha would teach in her course about antennas. We will not go in there. So we'll see what is analog communication, and then we will jump into digital. Have you seen this diagrams before? In which course? Signal communication system. So I will not go into much detail. I will talk about the things which is focused on Wi-Fi part. Right? Rest of the things I will not touch upon. And you see, analog modulation is one that was used for a long time. You have a digital signal, which I say a baseband, and that gives you your actual signal, what you want to communicate. Then what you have is an electromagnetic wave, which we say a carrier. And you see, what is the difference between these two? If this is high frequency as compared to this one. And then what you do is, when you transmit it, you modulate your carrier wave. So you interpose the signal on top of the carrier wave. Right? So you can see this. You interpose on this, the carrier wave starts modulating itself, and then this is what you transmit. This is very actively used in AM radio, but we are phasing out AM radio as well nowadays. This was used in AM radio. It is error prone and it is not resilient to distortion. Because of the primary thing, it is analog. And analog means it's a continuous signal, right? And if a small modifications here and there will affect your signal, how would you improve? Now, since you know this, what do you think we improve on top of this in digital communication, where you are more resilient to error? What would you do? You quantize the signal, right? You don't have analog signal. Instead of having all sorts of values here, right? You say, okay, I just have 2 values, right? So you convert your signal into streams of bit, you quantize them, right? And you have fixed levels of voltages, or only fixed values in terms of communication. So for example, if I have 4 2-bit communications, then I will have 0, 0, 0, 1, 1, 0, and 1. These are the only 4 signal values, right? Now, what is an advantage of this is, so if I simplify this, and if I say for 1, I will send a carrier signal. For 0 value of data, I will not send carriers. Right? So that is how, this is called amplitude shift gain. This is how I will communicate. So how does this become more resilient to error? Right. So you set a threshold, right? Anything below this threshold is 0, anything above this threshold is 1. And you have enough separation between 0 and 1, right? So that you will not have a point where it is, right? You are in a dilemma. What is this value? Right? So that's an advantage of having digital signal, right? So that's how you start communicating. You have digital signal, 0s and 1s. You have carrier wave, and one very simple way of doing this is, for 1 I will send carrier, for 0 I will not send any carrier, right? So at the reception, if I get signal, I will say it is 1, 1, 1, 1, 1. And if I am not getting any signal, I will say 0, right, for particular time duration. Right? And that's how I of it. Just moving from analog to digital does not solve all the problems. And there are bigger problems, or very fine-tuned problems. The first problem is we don't really want just 2 bits. 2 bits or 1 bit was a very simple example. You will have multiple bits. And when you start doing multiple bits, you have multiple values, right? And they will start coming close to each other, right? In terms of radio engineering, the challenges are signal travels over multiple paths. You go to a mountain and you shout and you get an echo, right? The voice, waves that you send, the sound waves, they hit on something and they come back to you, right? And these are the multiple paths that they take, and because of that, you get multiple copies of the one's transmission. But for us, it's not a challenge. When you are transmitting at a very high rate, megabits per second, and this becomes a challenge. What could be a challenge because of this? Can you guess this challenge? Multiple paths and multiple copies. What is the challenge in communication because of this? Right. So how would you do that? So he mentioned the right point. Okay. So let me tell to class what he's saying is: you send a signal, you send 1, and then you get 1, 1, 1, 1, 1, 1, 1. Right? Actually, the transmitter never transmitted 1, 1, 1, 1, 1. Right? So you have to eliminate all these extra ones. That's the first problem. How would you do that? Right, but if your echo is such that they come after a very long duration, right? If your walls are not so friendly, and they will transmit these ones, the copies immediately after first one, then how would you differentiate?
You send a stop after the last.
Before the stop, but how would that solve the problem?
I send 1 and then I send 0 if it is over.
Right.
I send only.
I get 1, I get stop, and then I get 1, and then I get stop.
Device will be limited. Whatever bit size is being sent to the device, the number of bits for the receiving device should be same.
But that's the chicken and egg problem. How do the receiver already knows that what I'm going to send? So we can't assume the memory because every device will have different memories and so on. You can't assume about the memory. See, the problem is you transmit something. This is the transmitter, this is the receiver. You get something here, and then there is a wall, right? And the signal hits and then comes back. That's the problem, right? And you want to detect this is echo and not the real thing. Right, but then you already have to know what is the distance and how much time will it take, right? And how would you communicate this if then they have never met? Right, but you can't assume the distance. Right? Transmitter and receiver are separate entities. They can sit anywhere, and they don't. So all these things you're saying, you are assuming one offline communication channel already exists, from where you do some sync. Right? But in this case, we don't have an offline communication. What you communicate is through this medium. Parity bit will not give you that information. Right? It just tells what if you have received 1, whether it is 1 and 0. That single bit. So let me give you a hint. So this comes, of course, with the fastest time, right? At the earliest, right? But this is also with some maximum power. Right? Whenever the signal comes directly, that comes with maximum power. And anything that gets reflected and bounces and then comes back, and these surfaces are going to absorb some signal, some power out of it. Right? It's not going to reflect fully. Right? And then this will be the maximum and earliest, and the rest of the copies will have lower and lower and lower and lower energy and more time lag. Right? So if you tune your filter at this end, so that you are looking for that maximum power and the earliest, right? Rest you start ignoring. You can still go wrong. I'm not saying that it is a full perfect solution, right? But because right, it just comes with a very minor delay, and power is almost equal, right? You get confused. And that's where you have an error in wireless. You have errors in wireless because this is the challenge. And nobody has a perfect solution for this. It's all probabilistic. Right? So this is one thing, multiple paths, multiple copies. Right, right. So this is, the tuning is actively going on. This is not a fixed threshold that you finally yet you fix it and you say, okay, this is for the lifetime. Right? Depending upon the transmitter and receiver. Not even that, right? Let me simplify the situation. If the transmitter moves from here to here, right, the power will change, the distance has changed, time would change. Right? You have to do it dynamically. Keep adjusting itself. So that's why mobile communication is hard, and that's why it took so much long time to get it correct and working. Still, we are not as compared to the wired communication, right? But this is one of the challenges. It's a good question. So another one is each copy of the signals gets different attenuation, like I said, path loss, and then it has reflection, refraction, diffraction, shadowing, scattering, all these technical terms. We're not going into detail. The bottom line is the signal bounces, comes back with a different quality, and the receiver has to deal with it. Right? Each copy of the signal may also have its frequency shifted slightly. Right? If you transmit at 2.4 gigahertz, right, by the time you receive the signal, there is a minor change in it, because right, there is air and medium in between that will add also. Right? And finally, there is always a background noise. Right? In physics, right, we are on Earth, right? There is atoms and molecules and air, everything is filled up with some material, right? And that will have its own electromagnetic radiations. Right? So that noise, your 2.4 gigahertz cordless phone will always, or your microwave, will always interfere with your Wi-Fi. Right? So this is the noise which is already there. And various channel models exist. But yeah, these are the challenges. And your wireless communication has to deal with this. So final received copy is the sum of all these different copies of the signal plus noise. You get this, and the receiver's job is to delete the noise, delete the multiple copies, and retrieve the original signal out of it. And it's a very hard problem. And that's why Wi-Fi is not so good. So let me give you some signals. You know about impulse functions and so. Good. Right? So this is to give you understanding so that you know when you look at the frequency terms, right? You know and you understand what is the capacity of this network finally. How much you can get out of this wireless network. Right? And where you hit the limit after which your wireless network will not deliver. Right? You should know mathematically how much is your capacity. So every channel you can describe mathematically. It's so complex, but let's simplify it. And what we say is it has its own impulse response H. Right? That will act upon the signal, and you will get back something out of that. So if in the frequency domain you look at it, if you have this input impulse, then by the time you get an output, it's like this. You get multiple frequencies, right, with multiple amplitude together, right? And what you want is finally is this one. So mathematically, if signal is X, the channel is H, the noise is N, then the received signal Y is H act upon X, right? And this is the convolution operator. I think you know the convolution. So if you don't know, that's okay. I'm not going to go into this more detail than this. So this is one mathematical function which acts upon the signal, and then it adds noise, and then you get back the signal, right? Y. And what you want is, how would you get X from this? If this is your Y, H convolution X plus N, right? How would you get X? Y is equal to, so what is X? Y minus N inverse of H. Right? So if the receiver knows what is the noise in the environment, thermal noise, because it is continuously sampling that thermal noise, and it knows what N is, it has to subtract it first of all. Get this Hx, right? And then you do again estimate what could be the convolution that is going on, and that's the dynamical. It is continuously changing, and you operate on that, and you get back the signal. Right? So this is how you get your original signal. So this is what the signal looks like. If you look at the signal at the receiving end, right, it looks like this. And so many frequencies acting upon this, right? There is multipath fading, so multiple copies that is acting at a very small time value. And because the signal bounces, comes back, it interferes with itself. So let me give you a challenge. I'm sending this 1, 0, 0, 1, 1, right? By the time the receiver is here, this one also gets reflected and comes here with some value, other value. Right? So that direct one and the one which got reflected will come at the same time at the receiver. Right? And they start interfering with each other. Right? Then this one will hit and come back here as one again. Right? So that's why the signal gets complicated like this. And as the distance increases, your signal, the transmission power that you see, it's getting less and less. Right? So as this distance increases, then you get less signal. The power increases. You have a question?
What is the difference between Y and H?
So Y is what you see as a signal here. And H is a mathematical function.
Previous slide, the definition was what you
Right?
what do you receive when you send one impulse? First line, wireless channel is
Right, this one?
first line.
Okay, wireless channel is described by channel impulse response H. What you receive when you send one impulse. Right. So H acts upon one impulse,
Which is the input.
and you define H in terms of that, not the whole packet. You send one impulse, one instantiation, right? Even if you give one bit, let's say it's 1 bit, and you talk about H in terms of that, not about the whole packet. Right? But finally, we will come to the packet. You will see 1 bit, then you will see 1 frame, and then you will see packets. Right? So you define H in terms of when you send one impulse, what will we define now H? What will be the one? So this is an impulse, and H will give you this. Right? After you apply H to this, you get this, and then you add noise. So if we are acting in an environment which is not going to give you multipath fading or any effects, what will be H? Right? The identity function. Right? So you send H like this, or you send impulse like this, and even if H acts upon it, you get exactly the same. Right? So that is the ideal scenario, but in reality, you get this one. So when you send one bits, it is distorted due to the channel, right? The 0 bits aren't exactly 0 now, right? Because even if you don't send anything, the noise will play a role there. And in our modulation, when we say I send 0, there is no carrier, right? But there is noise there, right? So there will be noise, right? And one will get the impact of the H value, right? Now the net effect is 0 and 1 are hard to distinguish between themselves, right? So as you see, this is the 1, this is the 0, and as they start coming close to each other, right? What is happening is you can't distinguish between 0 and 1. Even if you have digital communication, right, you are landing into the same problem again. With that, you cannot distinguish at the receiver what is 0 and what is 1. Right? Only hope there is if your receive signal strength is way more than your noise, right? You can do. There is a possibility of decoding. Otherwise, your signal goes for a toss. Right? You don't receive anything. Right? So your channel. So as you take your laptop and walk away from this access point, farther and farther, right? This is almost equal to the noise. right? And your laptop gives up at that point. Like, I cannot communicate. Right? But you come close to this one, your signal strength is way more than the noise that is already there, and you can decode the signal. So if received signal power and noise power are roughly equal, it's hard to recover the transmitted signal. This is, as you can see, if you and me we are distant, we are far apart, and if I talk, there is so much noise already in the room, we can't hear each other. Right? It's the same thing that happens in wireless, but in a very fine time level. So how do we say inside this room whether we can recover the signal or not? And we should have some mathematical way of saying whether I can receive the signal. So what I do is I say what is the power of the signal compared to what is the power of noise. Power is in transmission power. Okay. If I can shout loudly as compared to the noise, right, I can communicate with you. But my voice is not powerful enough, then I cannot communicate. So when we write this mathematically, right, hopefully the power is way more than the noise. That's why we use a logarithmic scale. And what we define now is signal to noise ratio in terms of decibel values in the log units. So this is, you should remember this for a long time. Right? SNR in dB is 10 into log of to the base 10 PS over PA. And you see how much is your transmitter power, how much is the noise power. Take a ratio, take a log of that, multiply it by 10, and that gives you SNR. Now, if I want to create any communication, let's say I'm going to Mars, and I want to send a satellite there. I want to send images from there. What should I know now? I want to send an image from Mars to Earth using electromagnetic radiations. What would be engineering I have to do? Right? And you can estimate the noise, right? If you know from Earth to Mars what is the distance, right? And typically what kind of waves are going around there in the background. And you can see you can estimate what is the noise. Then you have a transmitter on Earth and you have a satellite there on Mars, right? That is going to communicate. You know how much transmission power it can have at the most. Right? With that ratio, you know now whether it is sufficient enough or not in terms of SNR. Right? If your SNR is bad, then you cannot communicate. Right? So in wireless communication, if you talk to any EC person, the first thing he will ask you is SNR. What is your signal to noise ratio? If your signal to noise ratio is bad, there is no engineering you can do to receive your signal. Right? There is no magic in it. If P over S, PS over PL is 1000, your SNR is 30 dB. Right? So communication systems should have a minimum SNR threshold below which they cannot decode correctly. Above certain threshold they can communicate and you can decode. Below certain you cannot. Another unit, okay, now before another unit. So this is your signal to noise ratio, and you can also get this value in terms of dB for path loss and attenuation. The noise that you have, right, will also have some power. And you can take a logarithmic unit for that, and you can say, okay, my noise is this much, 20 dB. Right? And then you can use this one because it's both are on the log scale, you can subtract. Right? And it will act upon and will give you how much will give you a signal. Another way of looking at dB is dBm, which is your power as in terms of milliwatts. Typically, the transmission powers are not that much in terms of watts. Right? If you have a transmitter for which you know how much is your milliwatts, you can use dB. So this is the concept of SNR, which means how much your signal as compared to the noise. Right? So this can tell you if I transmit whether the receiver will receive it or not. And the first question. If my transmission power is below or less than the noise, right, I will not be able to communicate. But now, if I can communicate, second question, of course, we are interested in is how fast you can send. I can send data from Mars to Earth, but how fast? How many images can I send? So what do you call this typically? So when you say 2G, right, it has something which tells you how fast you can communicate. 3G will tell you something about how fast you can communicate. Wi-Fi, what is that word that you call? Data rate or bandwidth, right? How much you can send in per second. So SNR decides is it I can decode or not, but then you also want to see whether I can, if I send at this much rate, whether I can recover or not. If you see, if I'm transmitting at slower rate, I send this 0, a very long 0 and a very long 1. But if I can communicate fast, within the same time, I send 0, 1, 0, 1. Right? And faster, right, I have smaller value 0, smaller value 1. But there is a limit. Can you do it? Can you keep on sending faster and faster? And this is a thought question. I want to see if you can. Right? But then I can squeeze this way in a small duration. Squeeze it. It's not like I'm fixed that way. Channel. So what is the channel capacity tell me? You are also right. We'll come back. And this is mathematics. What you are saying is intuitive. Right? What is the channel's capacity tell me? Anybody remembers this theorem and how it applies here? Right, but it's about the speed now. We are talking about speed, and of course there is no magic in it, right? So we can't say infinite symbols in small duration. Right? If we can send infinite, that means right, we can communicate infinite data with no time. But that's not possible. Very good. Right. So combining what you said and you said, we'll come back. Right? But if you start sending too much, right, what will happen is you will step onto your friend's signal. Because your friend has got one frequency, you have got your own frequency. You send too much data, your carrier frequency, you have limits about how much you can operate, right? And if you start sending too much, right, it's like you can say in terms of another dimension. Right? This is, let's say, P1 and P2, right? And this is P3 and P4. They are communicating, and everybody gets its own pipe. Right? If you want to push more data, right, there is a limit on how much pipe can hold, right? And it can extend. But as your pipe gets fatter and fatter, if you start pushing more data, your pipe will actually step onto your friend's pipe, right? And your friend will not allow it because now you are interfering with him. So that's what happens in another dimension. You'll see it in terms of the signal processing. Right? But there is a limit. There is a limit on how much you can send. After that, you cannot send any faster. So let me see, do I have to go in detail about this? Okay, so let me quickly go through this. I'm not teaching you Fourier transform. Right? This is not the subject, but what does Fourier transform do is, you can transform any signal into discrete time signals of some frequencies. Right? To give you any signal, I can say this is composed of frequency F1, F2, F3, and what part of F1, F2, F3. I will give weights to that. And I can combine that signal. Right? So I'm transforming the whole signal from time domain to frequency domain. And the frequency domain, once you get the signal, you want to transmit it. Right? And at the receiving end, the signal will change. Right? The convolution operator will play the role, and at the end, right, you will get another signal. So let's not go into DFT. Right? So let's look at visually. This is your data signal. Its Fourier transform looks something like this. Right? You just take my word for it. Right? We'll not do the calculation and look at it. Data signal in frequency domain looks like this. Right? It is at one frequency it is maximum. There is a band on that frequency, and then other frequencies are very small. Right? your carrier wave is exactly one frequency. As you can see, this is only one frequency. There are no other frequencies. It's one sine wave with one frequency. So that's why in the frequency domain, you just have one impulse. Right? One frequency. Right? If you now do the same modulation here, you get this one. Then it gets shifted because this is shifting. So you get at F this data signal and its other parts. Right? So this is in the frequency domain, your this signal looks like this. Okay, so far good. Okay, now let me take a question. If I want to send more data, what would I do? My carrier is fixed. I cannot change the carrier, right? Because if I change the carrier, it's no more 2.4 gigahertz. If I make 3 gigahertz, 5 gigahertz, right? It's not Wi-Fi. So only thing I can change is the data. Right? So faster data means what? My frequencies. Right? So if I want to send more data, it will look like this. And I'm sending zeros and ones very fast. So far good. You're okay. With more data, right, you get this signal, and in the frequency domain, as you compare to this, what is the difference? With more data, what's happening? Right, you get more frequencies. Right, your pipe has got pattern. And you're using more frequencies in the frequency domain. Right? And when you add up now, right, you will have that same shifting, but a fat shift. Right, that band will be always be there. Right? And now what will happen with multiple transmitters transmitting at the same time? Can you guess? Right. Everybody is using so many frequencies. Let me just draw it here. Right? So this is one guy. Then you have the same frequencies here, right? And then this gets fattened, and this also gets fattened, right? They start getting overlapped. Right? In the frequency domain, when multiple people are transmitting with some data rate, we can ensure that after their transmission, in the frequency domain they are separate, right? But if you start pushing more data, the data rate increases. You're getting greedy. And you want to transmit more data, right? But what happens is in the frequency domain, if you look at the same signal, you get this fat band. That means you are utilizing multiple frequencies, and your friend also might do it, or even if he does not do it, you overlap some frequencies with him. Right? And at that point, you start interfering, right? And your signal strength goes down. Any questions on this? If you have doubts about this, just take a moment. So, first thing is, if I send the signal, whether you can decode or not, and that depends on the noise level and all the multipath effects. But if my SNR ratio, signal to noise ratio, is good enough, that means if I transmit, you will receive it, right? But then, if once that happens, the second question is, how fast I can say that you can still receive it. And it's not a question about one transmitter and one receiver anymore. If that is the case, I can transmit as fast as I can. Right? You should have the capacity to listen at the same rate. That's it. Right? But as we know in a Wi-Fi, right, we have multiple people transmitting at the same time. Everybody is using different channels. Right? And with that, what happens is, if one transmitter and receiver pair transmits fast, it will step in the frequency domain in another pair of transmitter and receiver, right? And it will cause problem for that pair, right? And that's why we cannot transmit. But this you can only see it in the frequency domain, not in the time domain. Yes. Loudly.
I am transmitting a kind of I guess you can play with some other.
Yes.
What happens?
Yes. No. So what happens is, if this thing happens, right? If you are starting to get overlaps, so the signal strength here is almost equal to signal strength here. Right? But this is noise for this signal. So your SNR gets affected. Right. It becomes hard to decode. Because right in that frequency domain, you have multiple signals with almost the same transmission power. It becomes hard for the receiver to decode what's happening. You get 20 megahertz channels allocated between the pairs of users. Right? And if you send faster than a certain rate, your bit rate becomes fast. After some rate, then your frequency domain signal will overlap with the neighbor signal and it will lead to data loss. Right? So that's why your transmission rate is always getting adjusted. Do you know what is the data rates in Wi-Fi that are typically happening? Typically, your Wi-Fi communication is happening. You can see this 1 Mbps to something about 4, 11, 54, and more. Right? So it is constantly changing. Even if you are connected to one access point, it is constantly changing the data rates depending upon how many other people are there. Right? So this you can see cannot see in very easily in time domain, and that's why you do all this mathematical juggling to get it into frequency domain, and then you can see the effect. Right? So other thing is your hardware capability to sample also determines. Right? You should have the same hardware as the transmitter and receiver to send data at some rate and receive it. So more frequencies mean you must send data with more samples, and the Nyquist theorem will also play a role. So I will not go. So you know what this Nyquist theorem is. We don't know. Do you know how many of you know what is Nyquist theorem? Okay, so what happens is if you want to transmit at a higher rate, you need to sample also at the receiver at higher rate. Okay, and as the sampling rate increases, the cost of the hardware also increases. Right? So that also plays a role, but that is the cost wise. So once you decide the bandwidth, this is the bandwidth of your signal based on the above two factors, you know how fast you can send the data. Right? And that's why bandwidth, data rate, how fast you can send, it's all the same. Right? If I tell you the data rate, you can tell me the bandwidth. If I tell you the bandwidth, you can tell me the data rate. If I tell you that you have 20 megahertz band, you can find out how much data you can send, how fast you can send, because there is a limit on that. Right? So all these terms gets, you can change between one and another. Right? So what is the speed of wireless channel? Right? So if you have, I gave an example of 1, 2, 4, 11, 54. Let's say you have 100 Mbps Ethernet. Then what is the equivalent of wireless channel? You should have that much of bandwidth to send that data. Right? If I give you very thin pipe and ask you to send me data at 100 Mbps, it's not possible. Right? You can calculate and tell me what should be the band that I should do to give you 100 Mbps. Right? If I tell you, I give you very narrow band, a band of very few hertz, and I tell you give me 100 Mbps, it's not possible. And because of this problem. So the rate at which you can send information depends on two factors. First is the rate at which you can send symbols, which depends on how much bandwidth you have in frequency. In frequency domain, how much bandwidth you have, that will tell you how fast you can send, right? And how effectively you can distinguish 0 and 1, which will depend on SNR. If you have too much noise, right, the noise will eat away all your signal, and even if you have very good bandwidth, a big bandwidth, it's also useless. Right? So you should have good SNR value and good bandwidth to give you good data rate. Right? So Bluetooth, what do you think in the Bluetooth is happening? Why is Bluetooth not giving you same amount of data rate? Bandwidth. So Bluetooth, the consortium, it has allocated a very thin pipe bandwidth in terms of frequency, as compared to Wi-Fi, which is also operating at 2.4 gigahertz, but it is giving you a fatter channel. Right? And because of that, Wi-Fi gives you more data bandwidth. And so this is in terms of Shannon's capacity. But I guess the intuitive explanation is more important. Right? You can see the channel situation and find out about this. So, questions on this? Let me just quickly summarize and then we stop today. So, I will be in the office after this. Some of you want to talk with me. I will be in the office after this one. And some of you want to collect your midterm papers. You can also do that after the class today. Okay. So, to quickly summarize what we discussed today, we started with the physical channel, the physical layer, right? And we will go layer by layer all the way to the IP layer for wireless. So, wireless, two things. One thing is the frequency and the other one is the bandwidth. In frequency, you see the lower the frequency, longer is the antenna size, but the distance is also longer. And as you increase the frequency, the antenna size decreases, but your communication range also decreases. So depending upon what communication you are interested in, you select a frequency and that will fix your antenna size. And so this is the antenna size. Then the multiplexing of user. If you want to multiplex users, you should see what other users are using the channel and how long you want to communicate will also be fixed depending upon what kind of frequency you are using. These are the common frequencies. Right. So we saw different types of antennas. Right. Then we saw you have a digital signal or a data signal. Sorry. Which looks like a sine wave, and then you have a carrier signal, and you modulate your carrier with the data signal, and it looks something like this. And this is what you transmit. At the receiver, you recover back the data by taking out the carrier. So the problem with analog communication is it's very susceptible to noise. If it's small noise, also the voltage will change. So that's why you quantize the signal, you fix the levels, and once it is digitized like this. This is more resilient to errors, and that's why we are going into digital mode of communication. Which one for this one? No, this is lost. Once you convert from analog to digital, right, there is something which we say ADC, analog to digital converter. Right? Once you convert that, then you are in the digital world. And then you don't have that line analog. Right? And at the receiver, you again get a digital and you show the digital. There is a cost. So it's lossy. Right? You incur that loss, but you get a better signal like this. Because your noise cannot affect it that much. So this is what it looks like now. Right? The data signal, the carrier, and right, one simple way is transmit like this. Right? So another challenge with this is multiple copies of the signal will interfere with each other because of the echo, right? And then you have to retrieve back your original signal, right? And in top of that you will also get some thermal noise which is there in the environment, right? You need to subtract the noise and invert the signal. So if you look at it in terms of functions, this is the channel response H that will act upon this input. And it will give you something like this as the output. H acts like this. It takes one for this particular channel and gives you output like this. And it will act upon every bit that you send. Right? And it will also add the noise. So at the receiver, you estimate the noise, you subtract it, estimate function H, and you apply inverse of H to retrieve the original signal. So if you see now, the transmission is this, the reception is this. And as you put more bits into this data, right, your zeros and ones and all these bits will almost start looking like each other. Right? So for that, the only hope is if your signal strength is more than the noise, you can decode it. Right? So once you have SNR, which is signal to noise ratio, more than some threshold, you can recover, otherwise it's all noise. Noise will eat up your data. Second question is, if I can send and receive, because noise is not much, but how fast can I send? And that will determine how much data rate can I have. For that, to understand this, we converted this to a frequency domain signal using FFTs or DFTs. This is really not for. So you see, every signal has a signature in terms of frequency. And it looks like this. The data looks like this, carrier looks like this, After modulation, the signal looks like this. As you put more data, into this, right, in the frequency domain, this looks fatter. Right? You are using multiple frequencies. Right? And as you start pushing more and more data, you use multiple frequencies, more frequencies, and you start interfering with your neighbor. Because your neighbor is also using some frequencies. And in this overlap with each other. And once there is an overlap, you will not receive the signal and your neighbor will also not receive signal. Right? So it starts interfering. Right? So there is a limit about how much you can send. Right? And if you want to send more, you give me more bandwidth. Right? And more bandwidth means you can. Right? So that's right. You should get, or to send more data, you should first know how much bandwidth you have. Right? And there is a limit. Once you fix the bandwidth, you have to fix how much data you can send. And then it also depends on the SNR, signal to noise ratio. If your noise is too much, you cannot send. So this is the summary. Okay, so let's stop here today.